Welcome back to our second speaker of the day, Karlheinz Gro. Speak about Gabor frames with totally positive windows.
Well, good morning. Well, I'm very glad to be here, meet old friends and a new community. So I will continue with Gabor frames and come and let's say with a focus on totally positive functions. The work on totally positive functions, windows and Gabor frames is started with Joachim Stöckler almost 15 years ago. Continued Joachim and Jose Luis Romero. So part of the topic will be joint work and so the plan is to focus on those parts where you can see how total positivity comes in and the arguments that work with total positivity. So everything else, the Fourier analysis, the Banach algebra stuff, I will completely ignore. But my goal is to show you how total positivity works in this context. And so the main object I'm going to look at, or I'm working with, is the sampling matrix. So for now, G is a window, generated template, X is okay. Well, I'm well, myself from you. Okay, so it will be the window that we have seen before, Gabor frames. X is some real parameter. Alpha, beta are the lattice parameters. I'm only talking about rectangular lattices. And the central object will be a matrix formed by taking window function G and evaluating it at points of the structure X plus alpha J. So this is where I will sample. And these are the shifts minus K over beta. In this case, in this sense, you will get a matrix. And I emphasize this will be an infinite matrix. The parameters, the labels J and K run over the integers. You could do more general versions where you take something, you replace this equispaced point set by some increasing sequence of points. And again, here you have equispaced points. You replace that by YK. But for now, we just deal with that. And where does that come from? Well, one source is the theory of sampling and shifting variant spaces. So briefly, what you look at is the span of integer shifts of the generating function G. And as soon as you impose a mild condition on G, then either you say, look at the closure of the span in LP, or equivalently, you say, I take all linear combinations with LP coefficients. And then the LP norm of the coefficients will be equivalent to the P norm of the corresponding function. So under mild conditions, that's the same. So that's a space. That would be a model for signals. And well, if you have a 1D signal, then it's, since Shannon, you want to discretize that, and you do that by sampling. So the relevant definition is you look at a discrete set in the real line, and you call it a sampling set if a function in the shift invariant space is uniquely and stably determined by its samples at the position space. Okay. So for a sampling set, you have a sampling inequality. So here's the inequalities and positive constants. What's important is here you have the sampled LP norm. So the LP norm is sampled. something discrete, and here you have the LP norm of the function. So the discrete sample norm should be equivalent to the continuous norm of f. And what's important is the quantifier that should hold for all f in this particular space. So I have a transition between continuous LP norm and the discrete norm. And for context, if you choose as a generator, the cardinal sine function, sine pi x over pi x, well, its Fourier transform is the characteristic function of the interval of length 1, centered at the origin. And so if you look at the space where you have the integer shifts of the cardinal sine function, then the corresponding space is the classical Paley-Wiener space of functions in L2 whose Fourier transform has support on the interval -1/2, 1/2. And that's the Paley-Wiener space. And there you are in complex analysis. And basically last century in complex analysis was in connection with signal processing, signal analysis, is devoted to understanding sampling in Paley-Wiener space. So in that sense, shift invariant spaces are substitutes for Paley-Wiener space. And when you look at the engineering literature, until up to 2000, every signal was band limited, belonged to Paley-Wiener space. Some point, I don't know, did they run out of new questions to ask? Or anyway, then suddenly shift invariant spaces became fashionable. And you do sampling in shift invariant spaces. One of the arguments is you want to model the data acquisition. There is no perfect band limited filter. And so in order to have more realistic models of data acquisition, you have to do something, and then you end up with shift invariant spaces. So what's the connection between the sampling matrices and sampling and shift invariant spaces? So, well, let's take a function in the shift invariant space and sample it and take its evaluation at the point xj. Then you get this infinite sum, and then you take the discrete LP norm. So what you get is this expression here. And so if we do sampling at arbitrary points, you get a matrix indexed by j and k. First point is the sampling point. The second index is the corresponding shift. And so the sample at xj is this matrix applied to the coefficient vector, ck, and then you take the LP norm. So what you get is this particular sampling matrix applied to the coefficient vector, and you take the P norm. So if you want to determine f and the coefficients uniquely and stably, you need a lower bound by the LP norm of the coefficients. You know, the some wide hypothesis on G, the P norm of the coefficients will be equivalent to the P norm of F. So in this way, the sampling matrix intervenes in the sampling problem. Now, the special case would be uniformly spaced samples. So in this case, the sampling set would be X, a shift of some, some multiples of integers. And in this case, you end up with the matrix I have here. So that's, oops, well, it happens. No? Okay, so in this way, the sampling matrix appears. And I'm only going to look only at uniform sampling. So now the second connection is Gabor frames, and I don't have to say anything about that. Marcus took all the work on himself. So there's just one slide on that. So we want to know when the time frequency shifts over a rectangular lattice form frame. So we want to investigate inequalities of this form. In that case, so, okay, so we want to understand double frames, goes more modest double frames over a rectangular lattice. You can, if you compare to the sampling and shift invariant spaces, then you will notice some conceptual similarity. Basically, here we sample a short time Fourier transform at the rectangular lattice, and the quantifier is now for all f in L2. So this inequality will lead to a representation or description of all L2 functions. So that's a whole field in itself, time frequency analysis. So what's that got to do with sampling and with these sampling matrices? So that's the connection. There's a mild condition on the generated G, should be continuous, and roughly speaking, whatever is here, it says that the function is majorized by a step function with, say, nodes at the integers, discontinuities at the integer. Oh, sorry, by a step function, yeah, step function with discontinuities at the integer. So that's some very, very mild assumption. And in that case, we have three equivalent statements. So the one statement, the one property that's of interest is when are the time frequency shifts over a rectangular lattice, when do they form a double frame? So under which conditions can we do time frequency analysis? The second condition is sampling in a shift invariant space. And here I take the shifts. So here we have two parameters. So here I take the shifts with the product of parameters times integer. And I take, so this is a uniform or equispaced shift with spacing alpha beta, but I might move them. And so the other condition is we have a sampling set in the shift invariant space with generator G sub beta. So there's a dilation involved so that I can take this shift invariant space with infinity. So Gabor frame over the rectangular lattice with parameters alpha beta is equivalent to equispaced sampling with mesh width alpha times beta is a sampling set for all x. So there's a quantifier here. This should we need sampling set for all x. Okay, that's a sampling theorem. And the third condition is this particular matrix. So I take the generator and evaluate it on the sampling set. On the sampling set x plus alpha j, take the shifts k over beta. This is left invertible on L2. The proof. So from here to here, I basically convinced you how that works. The proof of the equivalence of 2 and 3 is, well, depend on where you start with. It's just a clever application of Poisson's summation formula. But ultimately, it's behind the duality theory that Marcus explained before. And if you want to put that onto a higher level, you will bring in operator algebras and the rotation algebra. Are you going to talk about that?
A little bit, yeah.
Okay, so there are several points of view on this theorem. What I wanted to convince you of, persuade you of, is that this sampling matrix is a central object to understand what happens a shift in varying space and signal processing analog. So going from analog to discrete and we're back, so sampling and connection to the theory of Gabor frames. And to understand sampling and to understand time frequency analysis, the central object is an infinite matrix of this structure. So far, this is completely general. All you need is a very mild condition on the window function. Now, here enters total positivity. That's one of the central topics in this workshop, but I feel I should remind you of what a totally positive function is. So I call it function totally positive if the associated sampling matrix, so you take, has non-negative determinant. So for arbitrary number of points, you take increasing sets of points in the real line, two sets, and then you build the determinant, exactly the structure we had before. And the determinant of this matrix should be non-negative. So again, in red, I point out that the definition here is for finite matrices. When we started to talk about the topic, we had totally positive functions in L1. And I think if you live in the complete world of total positivity, then you make so many distinctions, and then probably you would call that a Polier frequency function. Okay, but since I never looked at anything but these functions and they're in L1, we just call them totally positive. So maybe that's for clarification. Okay, so here enters total positivity, and perhaps some of the main examples of totally positive functions, Polier frequency function. The one-sided exponential, in this case, it's an exercise to check that this function is totally positive. The other example is the Gaussian. Now there is basic fact, Schoenberg, if you convolve totally positive Polier frequency functions, then you still get totally positive functions. So the convolution of one-sided exponentials, finite number of convolutions, again, gives you a totally positive function. Typical example would be take the one-sided, so let's see, the right-sided exponential and the left-sided exponential, convolve, then you get the symmetric exponential Fourier transform of the Cauchy kernel.
Is it also stable on the limits then?
Yes.
Huh?
It's stable on the limits too, yeah.
Yes. So then you can take the Gaussian, convolve it with finitely many one-sided exponentials. That's one thing. The hyperbolic secant is totally positive. And if you want to see more exotic examples, that would be e to the negative x minus e to the negative. And if you want to know all totally positive functions in L1, you could take limits, let n go to infinity, but then you have to be careful about convergence, and you have to say a bit more about the, let's see, the inverses of the AJs would have to be in L2. So there's a complete characterization due to Schoenberg. I'm not going to say anything about that. Just for if G is totally positive in L1, so perhaps in your terminology, a Polier frequency function, then G has exponential decay, and the difference between L1 and not L1 is just a multiplicative exponential function. So from my point of view, so these are the prototypes of totally positive functions. And the whole story started when I visited Joachim and explained somehow what is known about Gabor frames. I mentioned these functions, Yeah, these functions are 3 or 4 functions for which there was some, let's say, complete theory for Gabor frames and for the frame set. And that's the beginning of the story. Let's see. So here is what is known. Say, no, when I say what is known, I mean complete results. The frame set where all the rectangular lattices can be characterized. Oops. So what's happening? So let's take a finite convolution product of one-sided exponentials. N should be greater than 1. Or let's take the Gaussian convolved with a finite with some one-sided exponentials. Here gamma should be positive and n can be anything. In that case, there's a complete characterization of Gabor frames. You obtain a Gabor frame if and only if the product alpha times beta is less than 1. The less than 1 is a necessary condition. There's a density theory of Gabor frames. You need enough information. In this context, enough information is the density of the lattice should be greater than or equal to 1. The size of a fundamental domain of the fundamental rectangle should be strictly less than 1. I leave out n equal 1 here. In that case, it's if and only alpha times beta is less than or equal to 1. So these are totally positive functions of finite type. I think you call them the Wieder. Hirschman-Wieder class. And okay. So for these 2 types of totally positive functions, there's a complete characterization. There's another result, arbitrary totally positive in L1, only a frequency function. And in this case, unfortunately, I have to still say that alpha times beta is rational. So for arbitrary Fourier frequency function characterization, you get a Gabor frame if and only if alpha times beta is less than 1. If you say beautify this result, you could say the set of lattice parameters alpha beta that generate a Gabor frame is open and dense after below the hyperbole with alpha times beta equal 1. So the set of lattices is an open and dense sets, but this doesn't cover all irrational. And for irrational, I have many proofs, but none of them works. But this is a result that holds for arbitrary Fourier frequency functions. And yeah, this problem has been around or bothering me for some time, and that's at least some result that closer to guess that for an arbitrary. So alpha times beta less than 1 is a characterization for Gabor frames. So a few remarks. These are, well, this is one theorem, but it's actually a long story. And for the Hirschman-Wieder class, so totally positive function of finite type, Joachim, I worked straight from the definition of total positivity. So the matrix is has no negative determinant. And and we worked with the Schoenberg-Whitney conditions to determine when is the determinant strictly positive. So we use totally positive. For the Gaussian type, so when you have a convolution factor that's a Gaussian, we didn't use anything about total positivity, but we used the characterization of Schoenberg. He characterized the Laplace transform of a totally positive function as a product or belonging to like a Fourier class and whatnot. So we used Schoenberg's characterization and some amount of complex analysis. And for rational Gabor frames, I came back to total positivity. And so if you know that the totally positive function is in a way a limit as n goes to infinity, you would like to try to take limits. And it's the obvious thing to do, but nothing has worked so far. If in frame theory, you try to take limits, well, at some point you have to quantify frame bounds, and that's even harder than showing that the frame bounds are positive. So if you want to take limits, you need some quantitative results, and they're hard. So what I want to show you is, so essentially what you're interested in is the left invertibility of the sampling matrix. So this is a matrix that it's associated to a totally positive function. The finite sections are, morally speaking, they are invertible. Sometimes you might have determinant 0, but you can handle that case. So, but we need some left invertibility of these sampling matrices. And there are two results about invertibility of totally positive matrices. One is, well, I refer to it as the Bohr's lemma from 1967. Joachim knew that straight away, and we have consulted that paper or the book where this is mentioned many times. So here we start with an arbitrary, totally positive matrix. So this means that all minors have no negative determinant. So if you can find a vector in Rn with maximum norm equal 1, so that its image is alternating. So in the image you have plus, so positive, negative, positive sign. And if you, okay, so and if the lower bound is delta, then then first of all, here, then the matrix is invertible, and the norm of that matrix measured in the maximum norm is dominated by 1 over delta. So the lower bound on that image vector. So never could do anything with that. And at some point, I found an infinite dimensional version of that. Surprisingly, this paper is hardly known at all, but it's the generalization of the Bohr's lemma to infinite dimensions. To me, this is a fundamental result. It's, I think, in Math Science, it's cited exactly 4 times. At that time, there was a flurry of activities because these people wanted to understand splines, and there was a deep conjecture in spline theory that they hoped to solve with total positivity. So here's the result. So the index set could be finite, or it could be positive integers, or it could be the integers. Finite, totally positive functions, or infinite totally positive functions. When I say infinite totally positive matrix, then it means that all minors have non-negative determinant. All finite minors have non-negative determinant. Now, so the infinite dimensional analog is, so you assume that the matrix is bounded from L infinity to L infinity. So it's bounded on a large space. If you can find a bounded vector on that index set, so that its image under the matrix is alternating, is uniformly alternating, okay? So the signs change, and this vector is bounded below, then this matrix is surjective, is onto L infinity. A remarkable result to show that some operator is onto. And this means that you can solve equation. It's about the solvability of the equation AX equals B. This is the best you can do. I think in the beginning there was a lot of discussion. I think there's even some error in some of the preliminary versions that the conclusion was invertible, and that's not onto, but it's not so clear whether it's one-to-one. So this is I think a fundamental result on infinite totally positive matrices. And now let's look how this can be used in the context of Gabor frames and in the context of that sampling matrix. And for that, I want to show you a simple calculation. When we take the sampling set to be a shift of the integers. So that is the critical density. And what happens if you take as your sampling set a shift of the integers? So here is the sampling matrix. We sample at x naught plus j. We are in the shift invariant space. So integer shifts by k. And so this is a typical function in the shift invariant space sampled at x naught plus 3. So now look at that. This is a convolution of the coefficient vector C with the so the matrix vector multiplication is a convolution of the coefficient vector with some sequence, and that sequence is actually evaluating the generator on a shifted integers, on the shifted integers. So the sampling matrix amounts to a convolution with respect with the coefficients. Well, for convolution, we know how to check invertibility. We take Fourier series and we check whether the Fourier series of the convolutor or of the convolver is bounded away from 0. So let's take Fourier series. So x naught is fixed in this case. So we take the Fourier series. Here it is. And okay, it turns out that the Fourier series of this particular sequence is a known object. If we take psi, so that's the variable of the Fourier series, the x naught in this case is fixed, but if we take that as a variable, then we get an object here denoted as C of G. In signal processing, that's called the Zach transform. In solid state physics, it's known as Fouquet transform. I think in number theory, it's called the transform of Weil and Brézin. Zach, he started out in solid state physics. He called it the KQ transform. Q for position, K for momentum. So we have two variables corresponding to position and momentum. And so this transform appears in several different fields. For us, it's the Zach transform. It's a fundamental object when you have some periodicity underlying, and whenever you use Poisson summation formula in some case. So the Zach transform appears in this particular case of a sampling matrix. So let's look at the Gauss. I had thought that Marcus would perhaps talk about that. But if you take the Zach transform of the Gaussian, then again a famous object appears. That's a version of the Jacobi theta functions, and so you end up in special functions. But what's relevant for us is that by symmetry, the Zach transform has precisely 1, 0. Well, it has 1, 0 in the unit square precisely when x and psi is 1/2. And otherwise there is no zero. So if we go back, we need that this matrix is left invertible, convolution operator invertible. And so we need that the Zach transform for fixed x naught is does not have any zeros, okay? Or bounded away from zero, which in this case amounts to the same. So if x naught, or if the x is not equal to 1/2, or 1/2 plus an integer, then this function does not have any zeros with respect to psi. So in that case, we get a sampling set, x naught plus z is sampling. However, there is at least one zero at x naught equal 1/2. And if you go back to the criterion, we need, so alpha beta equals 1. We need that this is sampling for all x, right? It's violated. So that means that if you take alpha and beta equal to 1, then the integer shifts of the Gaussian do not form a frame. That's a fact that was known, but this is sort of a byproduct. Now let's pursue a bit more totally positive functions. For the Gaussian, you can verify, well, not really by hand, but you can convince yourself that it has only one zero in the unit square. Now, there's a remarkable fact. If you take a totally positive function that's not a one-sided exponential, then the Zach transform has a single zero at some point of this form, x naught and the psi, the frequency variable, is precisely 1/2. So this is, I think this is a very, very important property of totally positive functions. Not sure it's known in this community, and this result evolved in steps. The first result is by Tobias Close and Joachim Stöckler. Here then to close extended, and for when you take limits, that's the final result. The final version is by Vinogradov and Litskaya. So the Zach transform of a total positive function must have a zero, and it's only one zero. So if we start with a totally positive function and take the integer lattice, then because we have a zero, then this argument shows that on the integer lattice, first of all, there's always something, some shift. So on the integer lattice, there's always a shift that's not sampling for the corresponding shift in varying space. This is not new. Wiener Janssen did that already, early 90s. But in a way, when we start with Paley-Wiener space and take Paley-Wiener space as the model of how results should look like and what you expect, then this is a price. Because for Paley-Wiener space, any shift of the integers will give you a sampling set. So here's a new phenomenon. Okay, so this is a model example, uniform sampling, and you. So now let me recall the result. So alpha times beta rational, and B is a totally positive function, no restriction. And I want to convince you or show you the arguments that go into showing that obtain a Gabor frame over a rectangular lattice if and only if the lattice parameters satisfy alpha times beta less than 1. So as I said, I want to highlight the role of total positivity, and I simply skip everything that also goes into that. So here's first of all, to work with the Zach transform as I defined it, we can normalize or dilate the generator so that beta is equal to 1 and alpha is strictly less than 1. That of totally positive functions is invariant under dilations. So I can do that. So that's a normalization. And then we have a totally positive function here. And I use the result that the totally positive Slack transform of a totally positive function has precisely 1, 0 at 1/2 and some x naught. I cannot say anything about that. And the first step is, well, we thin out the sampling set. Our sampling set is x plus alpha z. We thin out the sampling set to get something of density 1. So alpha is less than 1. So on every interval of length 1, I have at least a sample point. And on many intervals, I have a bit more. So I thin out this sampling set, choose a point in every interval of length 1 in such a way that I'm at a positive distance from the 0. Okay, the distance between samples is alpha less than 1. So if I make delta less than, I think, 1 minus alpha half or something. So if I choose delta small enough, I can do that. So then I label this extracted set by j plus delta j, and the delta j stays away from the 0 by a positive distance. I can do that because, let's see, the length of this interval is 1 minus 2 delta. And as soon as 1 minus 2 delta is greater than this alpha, I have at least 1 point in here. So then I consider the submatrix of the sampling matrix, and I beg your pardon that I still, again, call it P. So I thin out this arithmetic progression and just take 1 sample in each integer interval. So I look at this. And now the goal is to show that this extracted matrix is invertible on L infinity and on L1 and whatnot. So invertible on L infinity. Well, okay, footnotes, so we can, when I run out of time, I'll disregard them. But still, let me point out, there's still an x involved, and we should show this matrix is invertible for all x. And this thinning out, the sparsifying, depends on what the x was. But, so this argument holds for any shift. But we should be aware of these delta j's actually depend on the x here. So we have a great theorem that tells us when a totally positive infinite matrix is onto. Now, okay, so first I have to say if P is a polar frequency function, then this matrix is totally positive because all its minors, well, you have something increasing here, you have something increasing here, so all its minors have non-negative determinant. So total positive of infinite matrix is defined by finite sections. So in that sense, this is a totally positive matrix. So we have to come up with a bounded vector so that the image of this vector under the matrix is alternating. And well, you cannot come up with that either by trial and error. And well, what kind of sequence would you try? First of all, you know that you need the vector you try should also be alternating. That's a result that you know from finite dimensions that I mentioned it a bit later, the variation diminishing property. So if they're in the range, the vector is alternating, then in the original domain, the vector should be alternating. So the simplest alternating vector is -1 to the k. You can be more fancy, but I don't know how to find that. So we take the simplest alternating vector, -1 to the k. Plug it in here. So this is the matrix after thinning out. We apply it to the alternating vector. So now I said k equals k prime plus j. I do a shift. So if I set k equals k prime plus j, then the j cancels, and what's written here is delta j minus k prime. This is the only calculation, and I think we have to do it. So what's here is, well, we do a shift of the index set. You can take the -1 to the j outside, and then what's left here, well, -1 to the k is e to the 2 pi I k times 1/2. So what's written here is the exact transform of g at delta j plus 1/2. So the delta j is considered perturbation of the interior. So now we have made sure that the delta j stay away from the zero of the Zach transform. Okay? So we stay away from the zero of the Zach transform. Since the Zach transform of zero is only at x naught plus 1, x naught plus 2, this has, the sign is independent of the delta j. And since we stay away from the zeros, we can bound this below independent of the delta j. So we have found a vector whose image under that matrix is alternating and bounded away from zero. Conclusion from the theorem of Gabor, Friedlander, and Pincus, this matrix here maps L infinity onto L infinity. So this theorem is, I find it amazing, and it should be really be known. I think this is a powerful tool. So now we have onto. Now you do some magic. The spectral invariance. Spectral invariance refers to phenomenon that the spectrum of an operator is independent of the space on which it acts. So invertible on L infinity is equivalent to invertibility on LP. So there's a modification that onto is preserved. So once we have that the P maps onto L infinity, there's some magic that shows that P maps L1 onto L1. This is highly non-trivial, but I dropped that because it has nothing to do with total positivity. It's, let's say, spectral theory of operators. So now injectivity, and suddenly it turns out that this is a harder problem. And that's where, so the argument so far has nothing to do with whether alpha times beta is rational or irrational. Now here comes the observation. When alpha times beta is rational, then these perturbations of the integers form a periodic sequence, periodic with period p. And that leads to the fact that the matrix P, so this matrix here, so this is periodic with period P. This implies, after a short calculation, that this, sorry, this X is, I deleted it everywhere but here. So this matrix commutes with the shifts by P. So you have an infinite matrix that commutes with shifts by P. What to do? You divide into residual classes. You find an argument that I had before. When P is equal to 1, you find that you can decompose into convolution operators. You take Fourier series, so you can represent P as a matrix, finite P by P matrix, but you can represent it as a P by P matrix valued function. But for matrices, the funny thing, the fundamental thing is, if a square matrix is onto, it is 1-to-1. That is behind this argument. And when alpha times beta is irrational, then, well, there are some tools, but don't know how to use that. So anyway, surjectivity implies injectivity when alpha times beta is rational. And it's essentially boils down to knowing that for finite dimensional square matrices, injectivity is equivalent to surjectivity is equivalent to invertibility. Here we use a particular representation of this infinite dimensional matrix. So we have derived that P is onto one for rational product alpha beta. We use this property and can deduce that it's 1-to-1 on L1. That means this matrix is invertible on L1. And then again comes the magic of spectral invariance. Invertibility on L1 and decay implies that it's invertible on L2. So this matrix here, sorry, the X should not be there. Okay, so no matter how, I always waiting for the moment when the last misprint is still there. It happens, no matter how many times you proofread, there's always 1 or 2 mistakes there. Here it is, and before there wasn't. Sorry, so drop the X here. So this matrix is invertible. So it's bounded below by the 2 norm of C. And the original matrix is actually, we have more values here than here. So this is basically a larger sum. And so we have found the lower bound, which amounts to left invertibility. Upper bound is almost obvious. So that would conclude the sketch of proof for the case that alpha times beta is rational. And what I tried to show you is that how total positivity comes in. The rationality we have used only here. The onto part worked for, well, you see what we used and then you just check how much you can generalize that. So that is a sketch of the proof with the emphasis on where total positivity comes in. So there are, I find that when you go to totally positive cases in infinite dimension, there are many new questions arise. Well, obviously invertibility and injectivity is something that I personally am very interested in. And we have a tool to check whether such a matrix is onto. But for 1-to-1, it's not clear whether that is inherent in total positivity or not. So another thing is this question here that Joachim and I discussed early on. I presented the question to Mihai several years ago, and maybe this is a good place to discuss that further. And I was talking about total positivity, and one of the characterizing properties of total positivity is that they are variation diminishing. So in finite dimensions, that's a characterization. We look at this number of sign changes, and when you apply totally positive matrix in finite dimension, then the number of sign changes in the image is smaller. So the variation diminishing property. That's actually a characterization of total positivity. Now, let's go to infinite matrices. Well, clearly, the number of sign changes decreases, but we have the examples that I showed you, we have an infinite number of sign changes. So in that case, well, it's still true. We have infinite number of sign changes. It's trivial that the number of sign changes decreases. So you have to measure the sign changes in a different way. And I guess natural thing would to measure the density of the sign changes. So you measure how many sign changes as you would have on an interval of length n. You take the relative frequency and then take a limit. I'm so used to sampling theory, and there the lower boiling density is the correct density. I don't know what you would have to take here. Some density of the set of sign changes. And then the question is, does the density of the sign changes decrease in the image of a totally positive infinite? Well, I have no idea whether this is even true. There are some hints when we dealt with the Gaussian and the zeros of functions in the shifty invariant space generated by a Gaussian. There we know that the density of zeros is at most 1. Okay, so there's a relation to sign changes. So that's the only hint that this may be true in some form. No clue. So if we know that, then all our problems would be about Gabor frames would be solved. So we have spent a lot of time and energy on understanding Gabor frames. If we know that for infinite totally positive matrices, even those totally positive matrices that come from a Polier frequency function, then maybe it's not true for all totally positive. So this is a very, very general question. Is there some property like this? So if we know something like that, we'd be done with that program with Gabor frames and totally positive functions for a long, long time. But maybe there's time for discussion this week. And yeah, okay, this is maybe for entertainment. I thought, okay, it's time to stop. It's probably when a mathematician starts to deal with the Riemann hypothesis, the question of similitude. So I've done my work on that. So here's the Riemann zeta function. Here's the modified version, the Riemann psi function. That's what you use for the function equation, because psi of s is equal to psi of 1 minus s. And then when you look at Schoenberg's characterization of totally positive function and look at it once more, then you get this. So the Riemann hypothesis holds if and only if the Fourier transform of the inverse psi function is a Polier frequency function. This is just interpreting Schoenberg's criterion of Polier frequency. And I would assume Schoenberg knew this because he was married to the daughter of one of the eminent number theorists. He started out in number theory. To my knowledge, he never mentioned that anywhere.
In the
Okay, so
denominator, there's no I tau.
no, that's the whole point. This is about the Riemann zeta function on the real axis.
Yes.
That's the whole point. And it tells you this is completely hopeless because you want to know something about the Riemann zeta function on the critical strip, and you only use values on the real axis here. No, it's an entire function, but still, there's no complex analysis involved here, so it must be much harder to work with this criterion. But I think it's amusing that when you do go to positivity, you're right in one of the hardest problems ever. Okay, thank you. Here's some references.